Well, in this video, we're continuing what we were looking at in the previous video where we had just talked about F being a reflection about a line. Well, we're now going to look at another type of a reflection. F is a reflection not about a line, but about a point Q in the plane. If Q is the midpoint of the segment B prime, where, as always, I may not say this every time, B prime is just F of B, for every single point B in the plane. Okay, and how do we denote a reflection about a point? Well, the same way we did it about a line, except that instead of S sub L, where L is a line, we have S sub Q, where Q is a point. It'll be a given point. All right, we're going to use that definition of a reflection to draw the image of triangle ABC, which we have down here, under a reflection about the point Q, which we see right here. Okay, it's not very easy for me to draw this without just using what the definition is. So again, we'll say our sheet of paper is the plane P going infinitely in all directions. Okay, so how do I find, let's see, C is the closest point to Q, right? So let's start with that because it'll be the easiest one. How do I find C prime? This Q has to be the midpoint of CC prime, the segment CC prime. So let's draw this lightly. And if Q is the midpoint, we have to extend it exactly the same amount one more time. And that will give us C prime. Okay. Doesn't exactly look like the midpoint. I may have drawn this a little bit too long, but we'll get the idea. I'm not using a ruler and a straight edge and measuring these. Okay, now let's go to A. Let's connect A with a line segment lightly to Q, and then extend it exactly that same amount again so that Q is the midpoint. Is that about right? Yeah, maybe a little bit longer. We'll see. I'll call that A prime, F of A. So B then, we need to go draw the segment BQ and then extend it even farther in the same direction. Extend that line segment, basically double the size. And I'm noticing that my lines aren't very straight here. So assuming that length is the same as that, I probably didn't quite make it long enough, but you get the idea. Now, let's simply connect this line segment. AC is going to map to the line segment A prime, C prime. So let's draw darker A prime, B prime, C prime, this triangle. Okay, and maybe I'll shade the interior just to make it stand out a little bit because I have those extra lines in the plane there. So here's our triangle ABC. The reflection about the point Q of this triangle and its interior would be A prime, B prime, C prime. Okay, so that's how you get a reflection about a point. Okay, let's get some terminology here, a definition. Number 3, a mapping of the plane that preserves distances is called an isometry, which means same, iso, metry, metric, or same measure. Isometry. And by the way, if we continue that, it looks like this was an isometry. The distance from A to B is the same as the distance from A prime to B prime. Okay, so in other words, F is an isometry if for every 2 points in the plane, R and S, RS, now don't put the bar over it because when you just write RS, it means the distance from R to S is going to be exactly the same as the distance from R prime to S prime. And again, I'm not going to write this down every time, but R prime is F of R. S prime is F of S. So maybe I'll say that's equal to R prime S prime, just as a comment. I'm not going to do that all the time. Okay, number 4 now, we've got a lemma. An isometry, a mapping that preserves distances, also preserves collinearity. It also preserves betweenness, and it also preserves angle measure. All 3 of those things. All right, and it's a very simple proof. We'll show, now let's do collinearity and betweenness. So let's let f of a be a prime as always, f of b is b prime, f of c is c prime. And suppose that we have a, b, and c, 3 collinear points in the plane, and b happens to be in between them. We will prove that this is proving 2 things. That's proving that a prime, b prime, and c prime are collinear, and that b prime is in between a prime and c prime. That takes care of our collinearity and betweenness. That's what we're going to prove right now. Okay, so what does this mean? B is between A and C in the plane. By definition, you remember what that means? It means the distance from A to B plus the distance from B to C is equal to the distance from A to C. So that means AB with no bar over it, that's the distance, plus BC is equal to AC. That's just by definition of betweenness. I'm just going to write by definition. Okay, well, we are talking about F is an isometry. So distances are preserved. Okay, we know F is an isometry. So that means that AB is equal to A prime B prime. BC is equal to B prime C prime. And AC is equal to A prime C prime. That's by definition of isometry. And we know F is. We're given F as an isometry. And again, this first one was by definition of betweenness. I didn't write it though. Okay, well, what does this mean? If A prime B prime plus B prime C prime is equal to A prime C prime, that by definition means that B prime is in between A prime and C prime. I'm just going to write by definition again. The first and third lines are by the definitions of betweenness. Okay, so we proved that B between A and C, they're collinear and B is in the middle between them, implies that B prime is between A prime and C prime, so they are also collinear. All right, now let's prove angle measure. This is actually going to be very simple. Let's just take a triangle. You know, a triangle has 3 angles in it, right? Well, given triangle DEF, if its image under the isometry is triangle D prime E prime F prime, then we know that the 2 triangles are congruent. Why do we know that? We know that because 2 triangles are congruent if all 3 sides have the same length. So we could say by side, side, side. That's because it's an isometry. The lengths of the sides are preserved. Therefore, all of these angles are preserved. So just as a comment, we just proved that under an isometry, a triangle is mapped to an equivalent triangle. It's just mapped to another triangle that looks exactly like the original. And you can probably guess what this is. Note that a reflection, think of it as a mirror image. If it's just a reflection, all line segments are going to be the same size. So a reflection is an isometry.